So to proceed with cyclic model, one of the protagonists of cyclic model is the dark energy.
Yes.
What is this enigmatic thing, and what role does it play in the cyclic model hypothesis?
So dark energy from the modern point of view is nothing but the tension of these brains. So as we're all used to, if we have a surface like a rubber sheet, it has some tension, and so it has some resistance to being deformed. And when Einstein first developed theory of general relativity, he realized that space, ordinary three-dimensional space, could in fact have such a tension. It was perfectly allowed by his theory, and he called that the cosmological constant. Reason it was cosmological was that this tension has a very peculiar effect when you combine it with gravity. So we're normally used to thinking of the tension as causing something to shrink. But in fact, when you put a tension into Einstein's equations, and if the whole of space is full of this tension, it does the opposite. It causes the world to expand. And Einstein used this to make a static universe model. So what he did is he assumed the world was a sphere, three-dimensional sphere, and then the gravity of ordinary matter would make it tend to collapse, because gravity, matter attracts itself under gravity. This tension would cause it to expand, and he balanced these two forces against each other to have a static universe. Unfortunately, it was unstable, so if it happened to shrink a little, it would collapse. If it happened to grow a little, it would blow up, and his model didn't make much sense. So he quickly abandoned it. And then, of course, he regretted having made this model, because 10 years later, it was found the universe is expanding, and he should have just predicted that. The universe can't stand still, it has to expand or collapse. But so he then abandoned this cosmological constant. But we always knew it could be there, and in fact the surprise is, or has always been, why is it not bigger than it is? Why is the tension of space not huge? There seemed to be nothing in the laws of physics to prevent that. And there are all kinds of contributions to the tension. You see, even if you have space with no tension, and you start adding particles and fields to the universe, each one of those particles contributes something to the tension. And to end up with very small tension is really difficult. You have to somehow cancel the contributions from different particles. It's always been a huge puzzle why the tension is so low. Then in the late 1990s, quite strong evidence emerged that the tension is not zero. It's actually positive, and that we call the dark energy. It's nothing but another name for the same thing. So it appears that apparently empty space, just the space between ourselves and other galaxies, is actually full of energy. That's the energy associated with the tension of three-dimensional space. And from, as I say, from a modern point of view, this is entirely what you expect for a brain. If space is a brain, it has a tension. So the surprise is that it's so tiny. Why is it so tiny? Now, if you try to quantify how tiny is it, it turns out that it is 10 to the power minus 120. So that's 10 to the 120 zeros followed by a 1. Point, 10 to the 120 zeros and a 1. And so it's ridiculously tiny in the natural scale determined by gravity. But nevertheless, it's important enough that it matters in the universe today, otherwise we wouldn't have seen it. So it's very important for the future of the universe, because it causes it to expand faster. So whereas matter makes the universe slow down its expansion, this stuff speeds it up. So if we now follow, so we're currently 13.7 billion years old. If we follow another 13.7 billion years in the future, this stuff will really have taken hold, and it will have begun to dilute away the galaxies exponentially. and we wait a few more tens of billions of years, all the galaxies we see now, almost all of them, will disappear from view. They're just diluted away. We'll actually just see them go redder and redder as they're accelerated away from us, and they'll disappear. So we will be alone in an empty universe, surrounded perhaps by our nearest neighbor galaxies, but nothing else. And so people in the future, or scientists in the future, will be very puzzled by the universe. They'll find themselves in an apparently empty universe. They won't see the radiation left over from the Big Bang, because it will have been diluted away, and it will look very different than our universe today. So, faced with this situation of a universe which started from a Big Bang, which was indescribable, which ended up dominated by dark energy, which is mysterious, we thought we would try to see things from a different point of view, and that's how the cyclic model arose. So we had this picture that the bang could be a collision between brains, the brains would separate, and possibly they would come back and collide again. Now the question is, how does dark energy fit into that picture? And what we discovered was something rather simple, which is that when the brains separate, if they do have some dark energy, that causes them to expand in this dimension and stretch out and become very flat and very parallel to each other. And then this dark energy can actually decay. In fact, the dark energy can be the source of the force which brings them together. And as the dark energy decays, they will run together and collide again and make another Big Bang. And so what the dark energy does is it makes the universe empty, smooth, vacuous, and ready for another Big Bang, which will produce another universe, which is very big and very smooth, will be emptied out again by the dark energy. So in fact, the dark energy is like a stabilizer. If you didn't have any dark energy, these brains would collide. Their wrinkles and deformations they acquired in one cycle of evolution would be magnified the next time, and the whole universe would become more and more contorted and violent and disorganized. The dark energy keeps it all organized, and basically also provides the power which ends up causing the brains to collide, smooths them out afterwards. So it performs many functions within the model. Without dark energy, our model doesn't work. So, whereas in the conventional picture of cosmology, dark energy is not necessary, it's just an afterthought. It's something we have to add to fit the data. It doesn't play any kind of determining role in the model. In our model, the whole model doesn't work without dark energy. That's interesting. And then finally there's this big puzzle, why is it so small? Now I would say people working in the conventional framework have given up trying to answer this question. They say we will never explain why at the Big Bang, whatever produced the bang somehow made the choice, I'm going to fill the universe with radiation, matter, at huge densities and energies, and then I'll just add in 10 to the minus 120 of dark energy. Okay, no one will ever understand that. Why did they do that? Why did the physics determine this value for the dark energy? So they've basically given up explaining it, and instead they resort to something called the anthropic principle. Anthropic principle says maybe all kinds of universes emerge or are created, but we're not there in most of them. And so if the dark energy was much greater in magnitude, it would have killed us, or our ancestors, and so we wouldn't be here. This is a kind of appealing argument in some ways, but when you look more closely, it doesn't actually have any predictive power at all. It's more a rationalization. It's more saying, well, this problem is really one which we'll never understand. So I don't find that explanation appealing. In our case, if you have this picture of a very old universe, much older than 13.7 billion years, in previous epochs, the dark energy played a huge and even controlling influence. Then you have a huge amount of time for this dark energy to relax. If its values can change, and in these theories like M theory, everything can change. All the laws of physics are actually dynamical. All the parameters can change. Then this dark energy can change over very long periods of time. And maybe what's happened is the dark energy has settled down to a value which is just right to keep the universe cycling in a stable fashion. So it's as if you have an engine or a motor, and you have a source of fuel, and you switch it on, and initially there's some transient period, but it settles down at some value. And given that the universe is able to have long cycles, it's entirely conceivable that dark energy is settled. So we've published some papers on this idea, and it's a radical alternative to the standard view. But I think what we have shown is that technically we can construct mechanisms which, again, it's a sort of technical use of the word natural. We use it to mean when we don't have to dial parameters to ridiculous small values. We can make a model which will self-adjust the cosmological constant down to the small values like the ones we see today. It's only a model, it's not clearly true, but I think what the dark energy has done is made us really rethink our concept of cosmology and the Big Bang. Whereas people had seen the Big Bang as somehow, a one-off intervention which made a universe with everything we see. Now that picture doesn't seem to be coherent. Why would the universe work out the way it has if it was produced that way?
You also write that no form of energy in the past or the future ever goes out of existence, and that when cosmologists study dark energy today, they are also studying the same type of energy that dominating during intervals in the distant past, and that will dominate in the intervals in the far future.
That's right.
Could there be any information stored in the dark energy somehow about the past and the future of the universe?
Yes, definitely. So in this cyclic model, as the universe passes through one of these violent events, where it goes from being empty and full of dark energy, empty of matter but full of dark energy, it goes to being full of matter and radiation. What happens is that any signals or radio waves left over in the previous cycle do make it through. I mean, they will be there. You will need very, very sensitive detectors to read it. But in principle, it's all there. Nothing is ever lost, and so that's an exciting thought, that actually we could possibly communicate our discoveries about science to the future, and future generations who live in future cycles could one day receive it. What actually happens near one of these events is that all the particles we're made of, as the brains collide, they lose their mass, which is to say they become massless and they all move at the speed of light. So the only entities in the world which are present at the bang itself are moving at the speed of light. And so it would be a very unfamiliar world where all our particles, we would be sort of, we'd literally fall apart in a burst of radiation. And then immediately after the bang, we would be reconstituted into material objects. So it would be a very dramatic and violent event, but there's nothing to stop radiation going through the bang.
There is another interesting thing in your theory, and this is a big crunch.
Yes.
Is this big crunch just another name for the Big Bang? Are those the same things?
Same. Exactly. It's a collision between these two brains.
So maybe something more about the extra dimensions.
So, according to our current understanding of the laws of fundamental physics and our best unified theories, like the laws of physics we see in 3 dimensions are largely determined by the size and shape of the extra dimensions. So at every point in this room there's another 6 dimensions of space curled up in a little ball, a rather complicated little ball. It may have holes and brains are wrapped around it and so on, but a rather complicated configuration which we can study. We know mathematically how to study. And the detailed configuration of the extra dimensions actually fixes the physical laws we see. So electromagnetism, the strong force, the weak force, the different spectrum of particles we see, that is fixed by the configuration of the extra dimensions. So at one level, we haven't solved these problems in physics. We haven't said, yes, I know why there are 3 colors of quarks, or why electrons come with neutrinos, or we haven't really understood those problems. We've just converted it to another problem, which is, why are the extra dimensions the way they are? But that's progress, because you've taken an apparently insoluble problem and you've converted it into another problem, which may or may not be solvable. But from my point of view, what makes it interesting is that we've learned from this framework that not only do the laws of physics govern the universe, there are simple general laws governing the universe, but the universe governs the laws. In other words, the configuration of the universe determines what the laws are which govern the universe. So it's all very self-referential. And more to the point, if we understand cosmology, see, cosmology is the study of the structure of the universe. Well, we better include those 6 other dimensions. And if we understand their structure and why they assume the structure they did, then actually we've understood all of physics. So all of physics is determined by the structure of the universe. Then you say, well, where did all that come from? When was this structure determined? What physical processes? Well, of course, it came out of the bang. Mm-hmm. And so when this bang happens, you should not only study the gap between the brains, which cause them to collide, but the other 6 dimensions are doing something in this process at the same time. And it better be mathematically consistent. And maybe it involves changes in their configuration. They can change. And once you've understood the whole process of the Big Bang, maybe you will understand why the universe emerged not only with the structure it has, but also with the structure of the extra dimensions it has. And then you actually have understood all of physics. Mm-hmm. So the interesting thing is how all these questions have in fact become one question. Mm-hmm. And the question is, what bagged?
Mm-hmm. And do you think we will ever find a final true answer to this question, and that you think that universe is actually a cosmos that can be explained rather than a chaos that cannot be explained according to?
I don't know. I don't know if there are limits to knowledge. Some people, I think in the last few years, have become rather pessimistic, and they have resorted to this anthropic principle or other similar arguments to say, this is the end of the road for physics. Essentially, some people do argue that. I don't know. But I know that if we take that attitude, we'll get nowhere.
But you do state in the book that this is the best time for a cosmologist of all times, and that you are very thankful that you live at this exact moment. Why?
Because the last 10 years have seen unimaginable amounts of data collected from the universe. I mean, I was a cosmologist in '92, before the Kobe satellite mapped the universe for the first time. And at that time I was seriously considering giving up, because there was most of the discussion was based on prejudice, or there wasn't any good data. And so you had schools of thought, and some people were making galaxies this way and other people that way, and there wasn't any clear-cut data to discriminate between the theories. '92, the satellite went up and mapped the universe, and suddenly gave us a clean picture of the Big Bang. It was just phenomenal. And ever since then, the last 10 years, we've had this stream of high-quality data, And we now have the prospect of measurements of gravitational waves looking right back to the Bang. It's a unique period in human history where not only are we speculating about the origin of the world, but we actually have the data to test these theories. So I think to be pessimistic now is really ridiculous. I mean, people have been waiting for at least 2 millennia to answer these questions, and probably hundreds of millennia to answer these questions. We have the data. You want to give up now? You must be mad.
When the idea was born, you wanted to discuss it right away, but that particular night you were going to see a play Copenhagen in London, I read. And what made me thought of one thing, because the play Copenhagen is discussing ethical problems of science, of Bohr and Heisenberg. Are there any ethical implications or any ethical problems connected with a cyclic model? Could that somehow influence also the practical?
Well, okay, so I'll give you an example of what I consider to be an ethical problem. According to the cyclic model, the basic motivation of it is to try to understand what happened at the Bang, and to make mathematical models. And so our statement, first statement is that it's interesting to try to make a consistent mathematical model of the Big Bang itself. Now, some people don't even want to consider that. People say, no, this is beyond science. The start of the universe is not something we should be looking into. In fact, many ordinary people just say, look, you're getting into dangerous territory here. Explaining the Big Bang, that's religious territory. And so first of all, I'd like to say that it is an ethical statement, in my view, to say no, a subject like this is legitimate science. Not only can we do mathematics, we can do experimental tests, observations, and we should. And it's a wonderful and inspiring thing for people to think about. So I think it leads to a better appreciation of the universe. Even if you've got a model which is wrong, you're trying to understand the world. And in that process you appreciate it much better. But the second thing is again relating to this pessimism. Some people are arguing, even within physics, that we've reached the end of the road and that there are some problems too hard for us to understand. And I think for me that's also an ethical question comes into it there. Because I think it's our ethical responsibility to keep going and to encourage young people who may have better ideas than we do. And not to say science has maybe reached the end of the road. And so me it's actually a very deep belief that if you like, even if science is going to be much more difficult from now on, it's something which we have to do. It's something which we cannot avoid, which our children or future young people will never forgive us for giving up at this point. So I feel very deeply about this, that I guess people talk about the golden age of various subjects, and people say maybe physics has had its golden age, and the next one is biology, and the next one is, maybe people should concentrate on engineering or something now. And I feel very deeply that's not correct, because I think what we have learned from physics is that nature is remarkably simple once you see through all the details. And it's one of the treasures of humanity that we have this picture, a very simple picture of nature. And I think if all we do is to take care of that picture and appreciate it, and by trying to generalize it, we actually help people learn it, and even if we ourselves don't succeed in taking the next step, at least we will have kept the whole subject alive and interesting. So yeah, I care very strongly about this, and I think the interest in this kind of pure science and pure thinking about the universe, and honest thinking about it. You know, we have to be humble. We're making models. They're probably wrong. we should take delight when we've proven them wrong and go forth with more energy and make better models. That activity, I think, is something which is common to all of humanity. When I meet students from Ethiopia or Madagascar or wherever, they are all fascinated with these things. And whatever culture people come from, they share it. So I regard physics as being very lucky to have this tradition and this set of knowledge which needs to be cultivated and worked on. And if the next leap takes 10,000 years, fine, we'll wait, because it'll be worth it.
But do you see any possible negative consequences? Like, could that knowledge that if psychic model proves to be right, would that knowledge be somehow, is it possible to abuse it in some way? Would it be?
Very likely. I think all knowledge can be abused. And it never comes with a stamp saying safe, safe knowledge. There is no such thing as safe knowledge, I don't think. And it's up to people to use it wisely. So I don't think there are any intrinsic ethics in science. I think ethics is something one has to add to science and try and use it sensibly. Having said that, I think I'm not worried about any applications at the moment. It's rather, it's very far in the future where people may be able to manipulate things at these energies. At the moment, laboratory energies we can reach are about 10 to the power 15 times too small to probe any of the physics of the bang itself. If we could build an accelerator that was 10 to the power 15 more powerful, then we could actually do this in the lab. That's a long way off. I think probably our descendants will figure out how to do it one day. There's nothing that prohibits it, but I'm not too worried about it.
Okay. So maybe now we can proceed with African Institute?
Well, there'll be two things. One, that's just finishing this theoretical bit. You said that in the last 2 months you've been developing some new ideas, which we will hold back on until you want us to let the world know. But what
no, they're already on the internet.
And you're going to try these out in various places in America and elsewhere. What are these? Can you summarize these?
Yes, I can. So probably the single greatest breakthrough of the last 10 years has been the realization that gravity is describable in a way without using gravity. So, as I explained earlier, gravity involves the deformation of space, it's the curving of space, and that's always been our picture since Einstein. But in the late 90s, a young Argentinian physicist called Juan Maltesina made a conjecture which is extremely interesting and exciting, and for which there's now a huge amount of evidence that it's correct. The conjecture was that in certain situations you can take a chunk of space which is dynamical, so the space can warp and bend, and that's gravity. You take this chunk of space, but the space is bounded by essentially a container. I mean, there's a boundary of space. And on that boundary, you have some matter moving and interacting with itself. But the boundary itself is not dynamical, it can't change. There's no gravity on the boundary. It's literally like having, if you like, a rigid cylinder, but with rubber inside. So it's flexible inside, but rigid on the boundary. Now his conjecture was that you could describe everything that happened in the interior purely in terms of what was on the boundary. It's called a holographic principle. Holography, as you know, is when you map a three-dimensional object into a two-dimensional picture. And that was his picture, that the interior would be mapped onto a rigid exterior, and then you could use a description, you formulate a description of the world entirely in terms of what happened on the rigid boundary. And so this is very exciting, and it has been used to understand black holes, for example, when black holes evaporate and release their energy, how that process occurs, and how the information trapped in black holes emerges when they evaporate. But in the last few months, we've been using this to understand cosmology. So what we do is we map a dynamical universe, which is called the bulk. It's the interior, the sort of dynamical part of space-time. We map that onto a boundary, and we follow the system as it goes towards the Big Bang, or Big Crunch. So it heads to a singularity, and then we see what happens on the boundary, the singularity. What we've shown is that on the boundary, you can describe exactly how the system goes through the singularity. And once you've gone through, so essentially you take the bulk which has gravity in it, you map it onto this rigid boundary, you follow it till it hits the singularity, you follow it through the singularity, you come out on the other side and you map it back into the bulk, where it's again described by gravity. And so we've constructed the first complete model of passage through a singularity. And it's very fascinating. Not only, it appears, can the world go through a singularity and survive, which is again, and this is another picture of the brain collision, in fact. The two things are related. So not only can that happen, but also in the process of heading towards the singularity, it turns out that variations in the density of the stuff on the boundary are created. And these variations in density from place to place are of exactly the form we need to explain the variations in density in the real universe. They're called scale invariant. And so the variations we see, which gave rise to galaxies, are known as scale invariant, meaning they're the same on all scales. And scale invariance is a very simple property. It's also a reflection of an underlying symmetry. And what happened is that Maldaceno's picture, whereby gravity maps to matter in the bulk, on the boundary, that picture, the boundary theory, is automatically scale invariant. And so that scale invariance of the theory translates into the scale invariance of the density variations. So we've written a couple of papers about this, and there are many aspects still to be completed in the picture, but we think we have the means to do that. And if this is correct, if this picture turns out to be correct, it will be easily the most elegant explanation of the origin of the density variations, because it really all comes from symmetry principles, from gravity and from symmetry principles. So this is very exciting, and I'm presenting this work at several talks in the near future, and we'll see what the response is.
Okay, I've got three more questions, if you can bear it.
Yeah.
One is, you've worked with a number of Cambridge cosmologists, and two I'm particularly interested in, that is Martin Rees.
Yes.
And Stephen Hawking.
Yes.
Martin talked about Stephen, who was just slightly older than him.
Right.
How can you, as they say, compare and contrast those two?
They are polar opposites. Martin's great strength is in keeping abreast of the latest observational discoveries and the latest facts about the universe, and trying to piece them together in a coherent picture. And so Martin's contributions, I think, to cosmology have all been what I would say on the phenomenological side. He looks at the phenomena and tries to make a sensible model of the phenomena. Stephen's contributions have been the opposite. Stephen has been interested in fundamental theory, meaning that from his point of view, mathematical consistency and elegance is primary. It's in the tradition of Einstein. Einstein essentially wasn't too worried about data.
You know one of his quotations?
No.
He said if the data contradicts the theory, change
the data. So, he probably didn't mean that literally. But Stephen's work has always tried to employ the most advanced mathematical techniques to address theoretical puzzles and problems, paradoxes. So he would be much more interested in a sort of fundamental theoretical paradox than he would in the very latest observation. Having said that, Stephen has huge respect for the observations and interest in them. And should they become definitive, he might even believe them. But he doesn't really want to be, there's also a cultural difference between astrophysicists and theoretical physicists, by which I mean people studying particle physics, general relativity, fundamental theory. The cultural difference is that astrophysicists are usually very, very quick to jump on a new measurement. Every week there's a new type of star or galaxy or something detected, and astrophysicists will immediately want to say, imagine, what is that? And is a cloud of gas falling in, or is some dark matter swirling? Exactly what's happening. Theoretical physicists take a longer-term view of the world. It's not necessarily the right view. Discoveries can be made in a moment, but there's just a different culture. And Martin and Stephen represent those two cultures.
That's very, very helpful. The second thing is, you talked earlier about your dissatisfaction with Cambridge, but here you are, a professor of theoretical physics or whatever. You're back. Is it a good place to work?
Cambridge has been fantastic for me, personally, mainly because two things. One is the wonderful collegiate atmosphere. I was working in Princeton before I came here, which is an excellent department, possibly the best physics department in the world, but much more, I would say, sort of aggressive and self-promoting culture. What's so enjoyable about it is that colleagues are very willing to spend time to discuss or to share ideas or their knowledge or their expertise without any agenda. Just for the sake of it. And so that it has that culture which is excellent. The second thing which is great about Cambridge is the flexibility of the institution. That providing you fulfill a certain number of basic duties, which are pretty modest compared to other universities, you can do what you want. So for example, in coming to Cambridge, I had freedom to set up an institute in Cape Town and to raise money for it, and to bring in all sorts of allies and partners. And I don't believe there would be any other university in the world where I would have had that freedom. So Cambridge provides an open space, I would say. It's not too controlled, it doesn't have too much direction, if that isn't taken badly. But it does provide an open space, which is very, very valuable.
Which college are you at now? You're back at Churchill?
I've resigned.
Resigned?
Yes.
So you're not at a college?
I'm not at a college. I was at Downing College. I was at Churchill, but then after I moved here, I resisted joining a college. I didn't have time. And then I joined Downing I was a member of Downing for 3 years. They gave me a nice fellowship, but in the end I decided I wasn't bringing anything to them. I mean, I hardly went there. And I think the college concept is in severe need of renewal. I think it's become stale, and it's no longer, at least some the colleges, I don't know many colleges, but the colleges which I do know, some of them are no longer, I would say, a kind of genuine community of scholars. They've become too established, too less ambitious, and too many dinners.
Don't mention that. I have my second one in the week tonight. You mentioned your freedom to set up an institute in South Africa.
Yeah.
I heard a story which you can tell me whether it's true or not, that when you came back, now quite well known, if not famous, to your home on one occasion, your parents said, "That's all very well, Neil. I'm sure you're doing some really great stuff theoretically.
Yes.
But we're going to lock you in your room until you have an idea of what you might do usefully for South Africa, and then we'll let you out again." And you spent, according to this story, quite a long time in there, and then you knocked on the door and said, "I have an idea."
It's not quite true, but it has a grain of truth. I went there, in fact Herbert Huppert helped me go there. I wrote to Herbert and I said, my daughter is, I guess this would have been 5 years old. I'd like her to spend some time with her grandparents. Can I take a sabbatical and go to Cape Town? So she has 3 months with her grandparents. So he wrote back and he said, "You've got to come up with a better argument than that." So I said, "Oh, well, okay, I'll go and discuss possible collaboration between the University of Cape Town and Cambridge. How about that?" So he said, "Fine, I'll approve that as chairman of the faculty board, and off we go." So I went to Cape Town, and my daughter went to the local school there, and I was working in a little flat on the ekpyrotic universe. It was very wonderful. I had complete peace and quiet, and it was just excellent. But talking to my parents, the real thing is that I went to university in order to fulfill this requirement that I establish a link with Cambridge. And I said, "Well, what could I do?" And they said, "We need maths. We need maths. South Africa has a strategic problem. We don't have enough students coming through with high-level math skills. What can you do?" So we talked around it a little bit, and it very quickly emerged. There's the whole of Africa out there. There's got to be some good math students. Let's bring them all to South Africa, which is a nice place to come. Bring the best international lecturers in the world, and we'll create some mathematical stars. So it was just sort of obviously the right time to do it, because South Africa is respected by everyone, seen as a model for the future. So I had the idea, after meeting with people at the University of Cape Town, I had the idea, well, we just need an African Institute for Mathematical Sciences, just like the Isaac Newton Institute for Mathematical Sciences, and AIMS sounds a lot better than I&I as well. So I told my father about this, and we chatted about it a bit. He said, "Sounds great, I'm not sure we need mathematics." He didn't really get that part of it, but he said, "Sounds fine." And then the next day there was a rugby match on the TV, and so I said, "Well, I'll come over to your house and watch rugby." He said, "No, he said, "That's okay, providing you spend an hour in my office and you produce 1 page on the African Institute for Mathematical, then you can watch rugby." So reluctantly I came over, and indeed I spent an hour, and I typed out this plan for a maths institute, and I watched the rugby. Next thing I know, he's faxed this to all the people he knew in higher education in South Africa. And then I had to do it. Sheer embarrassment. So he really got the ball rolling in a number of ways. He made me do it. He then, when I'd come back from South Africa to Cambridge, he called me up and he said, there's a fantastic building on sale in Muizenberg. It's 50 yards from the beach. It's an 80-room hotel, Art Deco, built in the 1920s, magnificent building. And we have to buy it. And you have to set up this institute in this building. I said, wait a second, I haven't got any money, haven't got any supporters, this is all a dream, and he said, no, let's go ahead and get this hotel. And to cut a long story short, we bought the hotel for £65,000 for 80-bedroom hotel, using an inheritance me and my brothers had. So my brothers allowed me to use this to buy the hotel. And then I brought the 3 deans of science from the local universities to the hotel, and I brought them in and I said, this is where we're going to set up the best maths institute in Africa. And one of those deans got very excited about this. The other 2 were supportive, but one was really enthusiastic. And he's now the director of the institute. And so we converted this hotel. And through a lot of hard work and good luck, it has indeed become a most amazing institute.
What a lovely story.
Yeah.
Thank you. Was there anything else you wanted?
Yes, I wanted to ask, just if I can just have 2 more questions about AIMS. I just figured out what a wonderful name it is, AIMS. When you said it.
Right.
How is it doing now? What are the results of...
Well, AIMS is in its 5th year.
Mm-hmm.
We've had 4 graduations. We've graduated about 160 students so far. They come from everywhere in Africa. So currently there are 53 students from 20 countries, including 20 women. And we designed it so to really be innovative. It has a very interesting program, which is quite unlike normal postgraduate programs in universities. It's all geared towards problem solving and encouraging people to think for themselves and take initiatives and so on. So it's been sort of designed with that in mind. And the students have been incredibly successful. Last year, I forget the precise numbers, but we had about 48 graduates, and 45 of them are now on master's and PhD programs in top institutions. One is a lecturer, one is doing an MBA, the other one's working in an IT company. These students are the most highly motivated individuals I've ever come across. And given 9 months at AIMS, which they use to the maximum, I mean, they work 16 hours a day, they learn computing and modeling, learn how to write, how to give presentations, they take full advantage of it. And they become very successful. And so I think we sort of stumbled on, through necessity and through not having enough money, we stumbled on a model of education which is extremely effective, which is you get a bunch of people from many different backgrounds, countries, cultures, but with common intelligence. They are all very intelligent people. And you bring them together and you recruit the best teachers in the world, who are all willing to come to teach the best students in Africa. I mean, everyone's interested in Africa. They all say yes. And they all live in this hotel. And so it is a 24-hour learning environment where people will be up until 2 a.m. every night having impromptu discussions, tutorials, and so on. So it's a terrifically intense atmosphere. And after 9 months of that, these students are ready to go into anything. They can go into any field of science because they have all the skills that are needed. You see, this is what happens in an old institution like Cambridge. It develops layers of bureaucracy and rules and pro forma, curricula, which are almost fixed in stone. Whereas a new institution, can really jump to the cutting edge very quickly. And for me, there's a sort of purity about what's done at Ames, which is very exciting. That you think, what do we actually want to do? You're constantly thinking, what do we want to do? What's the most exciting thing? You have almost total freedom to do that. And the goal is very simple. It's to create, able people who can go into any technical field and contribute to it. The other thing is that by doing it in Africa, you automatically get students with very high motivation levels, because this is the chance of a lifetime for them. So that itself creates a unique atmosphere. So I think even though you might have thought Africa would be the last place you would develop the best model of postgraduate education in the world, in fact it's been the best place to do it, because you're taking students who are so keen. See, for African students you come out of the Congo, right? They are just as ambitious as we are. They want to be the next Einstein. Everyone wants that. But they've just had tantalizing tastes of it. And often quite good maths education at school. There are surprisingly good maths lecturers in the Congo. So these students come out and suddenly they're jumped to the cutting edge of science with the best lecturers. And boy, are they excited. And creative. They want to do things. We had a wonderful guy in the first year who arrived from the Congo, and he arrives, he says, I say, what do you want to work on? He says, I'm interested in quantum mechanics, I'm also interested in chaos, so I think I'm going to do quantum chaos. Okay, so he didn't know what it meant, of course. But he took a course on information theory at Ames, he took a course on quantum mechanics, and he wrote his essay using information, very sophisticated information theory, to understand quantum chaotic systems. And this was actually innovative at the time. And this guy as well, he writes poetry, he won a cookery prize in the International Students Association, he spent his time in schools teaching kids. He's just a sort of Renaissance man, and he's an African. And that's the kind of students who we are finding. And so my conception of Ames went from its being a sort of necessary step to solving a strategic problem, which is the lack of highly skilled people in Africa, more towards the conception that actually this will benefit science in the long run. Because I believe that when these cultures and people from different backgrounds and cultures come into science, they all bring a new energy and freshness, enthusiasm, and very likely some new ways of looking at things. And so I think this is a huge benefit to science. I mean, this year we have 5 students from Ames in the maths department. Previous to this week, you would essentially never see a black African in maths department. And the ones you saw were very isolated and felt second-rate and alone. This year we've got 5, and it's just the beginning. These students are on top of the world and they're having a fantastic time. And I'm actually hopeful that one of them will come at or near the top in the financial maths course here. Very brilliant student. And we've now set out, is our culture at Ames, that we're going to prove something to the world, which is that black Africans are every bit as good at science as whites. And now it's become a matter of principle. for example, there was this ridiculous statement by Jim Watson.
Yes.
I don't know if you heard what happened subsequently. His genome was sequenced and shown to be 16%
Yes, that's
African.
right.
But we sort of use this story to egg the students on, and they really take it on board. And one of our sort of dreams at Ames, which we repeat and which I will say at this 10th meeting, is that our dream is that the next Einstein will be in Africa. And the students love that. It's about self-respect. It's about seeing, the opportunities in Africa, not just all the problems, huge problems. But I think the world, needs to change the way it looks at it. We don't want charity. We want, dynamism and energy. And Africa is so much to offer the world. So that's really the philosophy of the SAMES project. Yeah.
You mentioned TED conference, so my last question would be that winning the TED prize means winning $100,000, but more importantly, you're granted a wish. Can you tell us what your wish will be, or is it?
Providing you don't publicize it before next Friday.
No, I won't. No possibility.
So the wish has two parts. The first is the dream. The dream is the next Einstein will be in Africa. And this dream may sound surprising or shocking. I mean, how could there be another Einstein? And how could it possibly be an African? But if you think about it, it's not really that shocking. Einstein was a Jew, and Jews didn't really get into science until around 1880. They were actually prohibited from going into universities in many countries in Europe in the 19th century. Some Jews went into medicine, very few went into hard science. But once they got into it, starting in the late 1880s, Hertz and Jacobi were the famous sort of physicists, mathematicians, then Einstein, Pauli, and then Born, huge numbers of them. And so that over 1/4 of all Nobel Prizes in physics have been won by Jews, and 1/4 of the Fields medals in mathematics have been won by Jews. So is that something innate to Jews? I don't believe so. I think, yes, there's some elements of Jewish culture which are helpful. A great respect for the written word, for study, which goes back to biblical times. But I think more important than that is that they were out to prove something. I mean, that the Jews were a suppressed group of people, had suffered horrendous, discrimination and oppression. And when they got half a chance, they wanted to prove something about themselves. Now look at Africa. Culturally, possibly, one of the richest continents on the planet. I mean, half of our music comes from Africa. Art, design. I mean, anyone who tells me Africans don't have logical minds, has never seen a bush mechanic in Africa fix a 50-year-old car, right? Or steam engines. There's still steamboats working in Africa. Why? Because they're incredibly clever, ingenious mechanics. I've seen a guy fix a radio, a valve radio used at the mission school, which I taught at in Lesotho. Completely untrained, but he kept that working, and he understood it in some way. I don't understand it, but he understood it. There is genius all over Africa. I'm convinced of that. I've met some very bright kids. I was tell you one story when I was teaching in...
We've got 2 minutes.
I was teaching,
for the wish as well.
Oh,
okay.
for the wish. I was teaching in Lesotho, and I took the kids outside to try to connect mathematics to the real world. And I said to them, okay, estimate the height of this building. And I thought they'd put a ruler and sort of, 5 meters, something like that. So there's a little kid, and he's drawing on paving stones with chalk. I thought, he's completely misunderstood. What are you doing, get the height of the building? He said, yeah, I'm doing the height of the building. He said, I measured the height of a brick, and I counted the number, and I'm